This lecture is going to go through refractive index that we'll start referring to as the lowercase n. Refractive index, or indices when I use the term plural, more than one. So the refractive index of materials. We're going to be comparing how light is going to refract as it goes from some medium, in this case air, into glass, or in this case this boundary here from glass into air. So this picture is going to be something we're going to be thinking about, we're going to be looking at. So refraction from glass into air, and this one here is refraction from air into glass. Here goes. So refraction is the bending of light rays. The ability of a material to bend rays of light is described by a value called the index of refraction, n. Refraction occurs when light rays cross a surface between two materials that have a different index of refraction. Thus the light bends as it travels from one medium to another. So here we have a list of just different materials in their index of refraction, where the vacuum of space has an index of refraction of 1.0, air has an index of refraction of 1.0001, ice 1.31, and so on. And notice diamond has a high index of refraction. And we'll talk about what that means and how that's changing and how light is going to refract a little differently as it travels from, say, from the air into different material. It's going to refract differently. They have different index of refraction values, or n values. So this is the point of emphasis here. So the angle of refraction. It's important that we get some practice applying the concept of the light path and then how the light is going to be refracted. So let's look, we'll do this kind of backwards here for a second. We'll look at this picture here and we'll try to make sense of what's happening. So let's say we're going to consider location A. That we have this light ray coming in at an angle, and it's going to strike this boundary and it's going to refract into the glass. So we know something. We know that air has a refractive index of 1.0001 and glass has a refractive index of 1.5. It's going to travel from a lower n value to a higher n value. So we can apply this up here. We can apply this rule here, that low n value to high n value, the refracted ray is going to bend towards the normal line. So at point A. So notice the boundary here, I draw my normal line, this dotted line here, and that my incident ray angle, right, my angle of incidence is going to be some value. We can call this some number here, but we don't have to put a number in. We can just see it as large, well, larger than, because after it refracts through the new media, it's going to bend towards the normal line. So the angle of refraction is going to be much less than, or in this case less than, the angle of incidence. So it comes in at some angle relative to the norm. It's going to refract at an angle that's going to be close. It's going to be smaller. The refraction is going to be closer to the normal line. So that's from low to high n values. If I now consider continuing to travel through here, the light's going to keep traveling through. It's transmitted. The angle of incidence, it's going to hit this new boundary. It's going to travel out into air. It's going to go from a high n value to a low n value. So the rule to this is from a high n value to a low n value, it's going to bend away from the normal line. So notice my angle of incidence is really small here relative to the normal line. It's going to refract or bend away. So the angle of refraction is going to be much larger. So here I have a small angle of incidence. Here I'm going to have a large angle of refraction. It's going to bend away from the normal line. So that's why drawing diagrams are very important, because it allows us to envision what happens when it travels from low to high and high to low. So we're going to solve some problems for refraction. So it's going to slow down from the speed of light, and that's what letter C is. So what is the speed of light that travels from a vacuum of space into water? Conceptually, it must slow down, but by how much? Well, in order to solve this, you have C, right? The speed of light in a vacuum provided, 3.0 times 10 to the 8th meters per second. Light slows down as it moves into a different media, causing it to bend or refract. The n value, right, the refraction index of water is 1.33. So I must divide 3 times 10 to the 8th, which is actually 300 million meters per second, by 1.3 in order to find the speed of light in material, in this case, water. So I'm going to get your attention up here. So the index of refraction, your n value, is going to equal the speed of light in a vacuum, right, 300 million meters per second, divided by the speed of light that is traveling in that material. So if we're going to find the speed of light in the material, I can actually just cross multiply these and find that the speed of light traveling through water here is going to equal the speed of light divided by the index of refraction, or the n value that's provided for you. So here I can do the math that the speed of light in water is only 2.3 times 10 to the 8th meters per second. It's still the speed of light, but only as it's traveling through water. It's slower than through the vacuum of space, but it's still really fast. I simply took 300 million, this value here, that's the speed of light in a vacuum, and I divided by the index of refraction of water of 1.33, and I get this value. So we'll have to look at some scientific notation here. So let's learn how to apply scientific notation from standard form and back and forth. So scientific notation can be used to turn 300 million meters per second, right, 300 million, into 3.0 times 10 to the 8th meters per second. First move the decimal until you have a number between 1 and 10. So we take this 300 million, we're moving this decimal, we're moving it in this case, we'll go to the left. And you'll see that there are 8 zeros, because I want to get 300 million into 3.0. And then so I move the decimal point to the left until I get 3.0, or 3. Finally, count how many places you move the decimal, in this case 8. You have just changed the standard form number of 300 million into 3.0 times 10 to the 8th. Notice there are 8 zeros by using scientific notation. So now we have enough information to solve the problem. We have an equation of the index of refraction equals the speed of light in a vacuum divided by the speed of light in a material. But I'm asking you to solve for what is the speed of light in a material. So that means we're going to have to change the equation. We're going to have to cross multiply to get the speed of light in a material to equal the speed of light in a vacuum divided by the n value, or the index of refraction. So that's how we're going to be using to solve this. So as we begin solving the problem from the previous slide, we know that c is the speed of light in a vacuum. That's going to be our 300 million. So we're going to solve this as the speed in the medium, equals the speed of light in a vacuum divided by n. So we know the speed of light in a vacuum here is 300 million, right? That's 3.0 times 10 to the 8. That's 300 million meters per second. Nothing travels faster, so there can never be an n value less than 1. So let's solve this. Here's the final piece to this solving. The speed in the medium, 300 million divided by the refractive index of water, 1.33. I get this large value, 225, 563, 910 after I rounded. So you can treat this, and I want to make sure we apply the concept of scientific notation here. For the sake of this exercise, this activity, I would say you could just simplify it as 2.3, it rounds up. 2.3 times 10 to the 8th meters per second. And it's still consistent with scientific notation. And it just says that it travels slower, traveling through glass with a higher refractive index. I've simply divided the speed of light to a vacuum divided by the refractive index, or the n value. Hopefully that makes sense. Moving on. So I do ask that you go ahead and get some practice with this. So solve the speed for the speed of light. So this is number 1. You can come back and find this slideshow and actually find the answer keys. But for now, solve for the speed of light traveling through different media provided or based on their n values. So here are the n values of some materials. So find the speed of light in air. Notice your n value is 1.0001. So remember, solving for speed of light in a material is going to equal the speed of light in a vacuum divided by the index of refraction, or n value. So you're going to solve for air, ice, water, glass, and diamond. And understand that as I increase my n value, I'm going to be decreasing the speed of light through that particular media, because the light has to be absorbed and re-emitted through the denser material. There's just more stuff in a volume, or in an area here. So here's slide number 2. Once again, the answer key will be able to be accessed later. So here's some more different materials, and let's make sense of light traveling from air into water. Notice, air into water, we have a low n value traveling into a higher n value, right? Air has a 1.0001 n value, and water has a 1.33 n value, and it's going to follow the rule of low to high, a low n value to high n value. It's going to bend towards the normal line. So that means this interior angle, my angle of reflection, remember, measured relative to the normal, it's going to refract or bend towards the normal line. So angle 2, or theta 2 here, is going to be less than my angle of reflection. So in this case here, or my incident angle is going to be greater than my angle of refraction measured from the normal. So if we apply the same concept, why is it we see a fish or something that's in water in a different location? Remember, that light is coming out of water into air to our eyes. So it's going from high to low. So look at how this works. Light reflecting off the fish is going to travel through water, higher n value, 1.33. It's going to refract when it reaches the boundary of air. And we're going to see it if it goes from high to low. High to low, it's going to bend away from the normal line. The normal line is always perpendicular to the surface of the boundary, or this interface here. And it's going to refract at a higher angle. And we're going to perceive it as being over here. Right? We've appeared, but it's actually here. The fish is here, but appears to be here. So the next part of this activity here is complete the following by determining which direction the refracted ray will bend, either toward, away, or stay the same as it travels through different media. So here's just some examples that you could apply to this picture here. So here's solving for number 3 here. And this is a little more complex, but I think we're now ready for it. If N1 is the material, here's an N1 and here's an N1. So it's going to go from N1 is some media, N2 is a different media, and N1 is back into the original. So N1 is a material that's different than N2. Which material has a greater refractive index? And how do you know? I'm going to ask that you pay attention to the angle relative to the normal line in both circumstances. So when the light ray travels from N1 to N2, the angle is going to do something. So make sure you're paying attention to how to read it and how to solve it. When the light ray travels from N2 to N1, the light ray speed does something else. So we're looking at what happens when it's traveling a difference of n values. And you can always go back to applying this concept. It's either going to bend away or towards based on high to low n values. So you have to use a little bit more information or some other information. So let's say, for example, that N1 is water. What material, based on the list, could N2 actually be in Y? So you'll use this to make sense of it. So invisibility cloak. This is kind of an interesting concept of the glass rod shining into, or excuse me, is resting in here to stir in vegetable oil. And we can't see it. It almost becomes invisible. Can you explain why that occurs? Well, it actually has to do with what's called the optical density. That materials that transmit light both reflect and refract light at their boundaries. If the amount, or in this case, the amount of reflection or refraction is based on the index of refraction, n value, which is what we've been talking about. The refractive index of the media the light is traveling through. When light is traveling through the air and encounters a new medium, some of the light reflects and the rest of the light keeps going and bends or refracts as it moves into the new medium. However, when light travels from a low n value to a high n value, right, the index of refraction, the speed of light decreases. Every material has an index of refraction that is linked to the speed in which the light travels through it. The higher the refractive index, the slower that the light travels through it. So back to making sense of this picture here, and you can still kind of see it. But the smaller difference in the n values of the two media, the less light gets reflected at the boundary and the less light gets refracted. So when the two media have the same n value, no reflection or refraction takes place. Thus the object becomes invisible. So we can say very confidently that the glass rod and the vegetable oil have the same or pretty darn close to the same n values or refractive index or indices. Vegetable oil and glass, the Pyrex, have nearly the same index of refraction, about 1.474. So often the index matching is not perfect, but they are very close. The glass rod doesn't completely go away, or you can kind of get a glimpse of it in here, but it does become a ghostly image within the vegetable oil. And we're going to take this one level deeper, and this is called Snell's law, and this is where we'll end with this. Well, I've got one more slide after this one. So Snell's law is also known as the Snell's-Descartes law and the law of refraction. It is a formula used to describe the relationship between the angles of incidence and refraction. When referring to light or other waves, passing through a boundary between two media, such as water, glass, or air. So we know this rule, and we know that N1 and N2 imply that you've got two different media. So if we view the picture, the fast medium right here is simply a small refractive index, right? Low refractive index, low n value. Whereas the slow medium has a large refractive index, right? We know this by now. The greater the n value, the lower the speed. The speed of light ray changes as it enters a new medium with a different n value. The speed change leads to refraction. So we're going to go back to applying Snell's law and really comprehensively understanding why this bends, why we see the spoon in water, in a glass of water, why we see it completely, let's just say, it almost looks like it's broken. So why does a spoon appear to be bent? Well, different media tend to have different refractive index, or n value. The glass, the water, and the air all have different refractive indices. So we see the spoon as if it's bent dramatically as a result of Snell's law being applied. Reflected light coming off the spoon that reaches our eyes has refracted as it travels through the different media. We only see that light, so the image we get is a result of that light.